All right. Or nope. Gutierrez, yes. In, yes. You're sorry, yes. Matter, yes. Muddy, yes. Matter, yes. Prieto. Yes. Ralph, yes. Ramirez, yes. Reading, no. Service, yes. Stead, no. Valencia, yes. Wilford, yes. All right, so let's go ahead and get going here. As usual, if you go into your course overall, if you click on the link for the second exam, you will find the keys for all of the versions of the exams. It'll also tell you on what page we covered every single question on that exam. If the message isn't already getting through to you, I do not curve courses. Over the summer, I had all but one A, B's, or C's. So if I have a semester where I have 50% F's, I'm covered because my average is good. Is your average good? Are you doing what you need to be doing? Because looking at the homework scores, folks, people waited until the last possible day to turn in homework. You know it. I know it. I pull the scores once a week. If you are not keeping up with the course material, it will absolutely swamp you. I'm not trying to be mean to you. I'm not trying to scare you. I'm just telling you the facts as they are. And that is that if you don't keep up with the material, it's not going to be a pretty picture. So moving forward, I will, in a little while, talk about the exam. The key is already there. I'm not making any adjustments. I'm not curving anything. You get what you get. You earned what you earned. If there was anything on here you'd never seen before, I might have felt a little bad, but that wasn't the case. So if you have an issue about how you're studying, then please see me. But I will tell you that by waiting until the very end to work on your homework, that's not really studying. That's cramming for an exam, and you can't do that in this class. One of the things that I asked you guys to do was to take a quiz on, is it an acid, base, or neutral early on, which meant that you needed to remember the idea of strong electrolytes, which things can break apart and which things can't. That came back to bite people in the butt more than once. I can't tell you how many people told me that this strong acid stayed intact in a net ionic equation. It does not. I can't tell you how many people told me that nitrate was a part of that reaction. It is not. It's a neutral ion. If you don't take the time to hammer out the things that I try to get out there early, then it's going to be a problem for you. So I saw a lot of things on this test that honestly I expected to see. So let's have a look at new material and get your feet underneath you for the new stuff. Now, a little bit of this chapter is stuff you have seen before. Some of it is not. Molarity, you've seen before, but you probably have not been really careful with the terminology. In this chapter, it's going to be really important that you know what it is that you're describing. Molarity, capital M underscore, or if it's bolded capital M, then that's your symbol for that. That's moles of solute per liter of solution. This is the only one that depends on the total volume of the solution. Now, we like molarity because when we're in the lab, we're measuring total volumes of solutions. And it's easy to create a solution that's in a molarity, and it's easy to measure it out. The downside to molarity is that it changes with temperature, because as you know, as you increase temperature, it increases the volume of your solution, and therefore your concentration isn't going to be what you thought it was if you measure it out at some temperature other than the temperature at which it was prepared. And so that's why in this chapter we don't use molarity very much. It's used all the time in all the other chapters, but in this chapter they start introducing a couple others that can be independent of temperature. One of them is molality. This is one you haven't seen before. Molality is moles of solute per kilogram of solvent. He's the only one that relates to the solvent. Everybody else, all of the other fractions in this chapter are based on the total solution. It's just that it's not based on the volume of solution anymore. They're usually based on the mass of solution. This one's weird because he's the only one that relates to the solvent you're using. So it's real important that you are paying attention to that. Mole fraction. Like any fraction, it's part over the whole. It's just that it's moles of one of the components compared to the total moles. Mole fraction is actually symbolized with the Greek letter chi, but my printer doesn't have that functionality here. Now, because it's based on a component, it could be any of the components. And so if I were talking about the mole fraction of solvent, for example, that would be based on the moles of solvent over moles total. And I don't know why this page return didn't happen. So cross that part out. This is percent by mass. So moles fraction is based on which substance you put in here. Mole fraction of solute then would be based on the moles of the solute over the moles of the total solution. It's a fraction, which means it's a decimal number. I know that I can sum my mole fractions, and that has to equal 1 because all fractions have to add up to the 1 whole. Mass. Percent by mass, you guys have been doing since high school. This is as expected. This is mass of the solute compared to the mass of the solution. And because by definition, something percent means we're taking this fraction, solute over solution, we're saying, well, how would that relate if the denominator were 100? Because that's what percent means. It means we're dividing by 100. So if I wanted to solve for percentage, I would have to multiply by 100. Would you agree to that? Now, there are two related concentrations to this, and we use these units if they're extremely small concentrations. If you get a letter from the JEA, they'll talk about the water quality, and they have to send you an annual report to your home. And in that water quality report, it should be giving you values in ppbs or ppms, because if you have anything at a higher level than that, you have some massively contaminated drinking water. And so these are very low concentrations. Parts per million means that we want to relate to what would it be if it were a million? But it's the same ratio as percentage. Percentage just always means 100. Per million means per million, mean divide by a million. So I would take this same fraction and multiply by 10 to the 6th to get my parts per million. And if I wanted parts per billion, I'd be multiplying by 10 to the 9th for the same reason, because this is what a billion is. So what we're first going to do is look at these concentrations because A, most of them are not temperature dependent. B, depending on how you use or you're given a solution, it may not be in the units you need. For example, when we buy solutions from our manufacturers, very commonly the concentrated acids are not expressed in molarities. They're expressed as percentage solutions because it's easier for the manufacturer to measure purity based on percentages. And so we need to be able to take that percentage and convert it into a concentration. Sometimes you have information about the solution and you need it in different units to be able to use it in a calculation. And so that's why we're going to spend some time on working with these different units of concentration. Now, we're going to talk about some of the weird things about these in a couple minutes here. We'll come back to the parts per million, parts per billion, common substitutions. But we're going to work first with what the pure definition is, because if you know the pure definition, you'll be able to work with any of these. Now, these are honestly not hard, but it does matter that you know the definition. If you don't know the definition, then you're not going to know what you're given. So I create a chart for myself. You don't want to use my chart? After today, you don't necessarily have to, but I would recommend highly that you do, because it's going to help you to organize your thoughts. And my chart is going to talk about what do I know about the amount of solute, what do I know about the amount of solvent, and what do I know about my total solution. Because we know that the total is a mixture, and these are both pure substances. We're typically going to be given information about mass. We'll be given information, we need information about moles. And in this instance, we're going to need to know about volume. And then the last line is just for reference information. Because if I'm going between mass and moles, I'm going to need some references. So this is typically going to be my molar mass for these two pure substances. And for the mixture, it's going to be my density. Okay? So what we're told in this instance is that we have a 1.0 moles per liter, because remember that's what molarity means. More importantly, moles of solute, since they name the solution as KCl, that's our solute. So when you're given molarity, you are given a fraction, actually. You're told two pieces of information. You're told about how much solute you have, and you're told about what your total solution volume is. So in this problem, because we were given molarity, we were given moles of solute, we were given the volume of the solution, just because of that information. That if I had 1.0 moles of this solution, then I would also have 1 liter of it. Are you with me so far? Because that's what molarity means. It's a ratio. So if this number is 1, it's implied that this number is 1 by definition. Now, they also gave us a density. Density is 0.99 grams per milliliter. Remember that density is talking about, in this case, the total solution. So based on how they name the solution, we know our solute is KCl. Since they didn't tell us anything about the solvent, we have to assume that it's water. Because most solutions in this class are going to be aqueous. Not all of them, but most. If there were any other substance, then they would tell you that. So in order to go from moles to mass, I need to know the molar mass of potassium chloride. Periodic table says 39.0983 for potassium, 14.0067 for nitrogen, and 3 times 15.9994 for oxygen. Gives me a molar mass of about, KCl. Sorry. 35.453 for chlorine. Yeah, I've been using the numbers a few years. All right, so I know that the molar mass for this is 74.5513 grams per mole. We need to do the same thing for water, 18.0158 grams per mole. Again, how do I get the molar mass for water? Yeah, two hydrogens at 1.00794 and one oxygen at 15.9994. Use good numbers here. When you're working on your homework, it matters that you use their periodic table. So just a matter of interest on that topic. If you go into Pearson, under Resources, periodic table. You've never noticed that up there? There it is. So it matters that you use there. If you click on a particular element, it'll pull up. All right, so we know that information. So here's the trick to this chart. If you know two things in the same column or two things in the same row, you can find a third easily. So what I know right now is that I have 1.0 mole of KCl, and I know the molar mass that says for every 1 mole of that substance, there's 74.5513 grams. I know two things here, so I can find at least another piece of information. I've got 1 liter, and I know that there's 0.99 grams per milliliter. Now, right now, milliliter isn't going to cancel. Would you agree to that? But I know that milli means 10 to the minus third. So apparently that's going to be 990 grams. Now, feel free to tack on another one if you can't remember your metric prefixes, but you could always substitute in for a prefix for its number equivalent. Otherwise, you can say, okay, there's 1,000 milliliters in a liter, whatever it is, what magic you get to deal with that unit. 990 grams. So now I have the ability to solve for what? It's like Sudoku. You can't find moles of a solution because it's not a pure substance. You can find total moles because there's no such thing as a molar mass for a solution, right? It's a mixture. What could you find? I can find the mass of water. Would you agree if I have two things in the same row, I should be able to find the missing piece? If it adds up to a total right? Solute plus solvent has to add up to that total mixture. Then I know that this one's going to be 990 minus 74.5513. $916.5487 maybe. Are we okay? Now what can I find? Now I can find the moles of water, because now I have two things in that column. So anytime you have two things in the same column, you can find the missing piece. So again, mass over molar mass, 916.5487. Yeah. Okay, what did you get? I'm willing to 915. There you go. Yeah, sorry. 87. Morning brain. All right, so that many grams, and you can see I'm doing it in my head here, 18.0158 grams for every mole. How many moles do I have then? Bless you. Sounds about right. So what's the only missing piece of information? Total moles, which is what? 51.81, because these have to add up. So these two columns will always sum to the solution. But depending on what you have, you might have to be solving for the other thing up and down a column. You know, it might be addition, multiplication, it might be division. You just have to check and see what it is. Now, with that information, if you fill this chart out, you now know everything you could possibly need to find any other concentration. Because now it's just a matter of what are our definitions. For example, we had molarity. We want to know molality, mole fraction, percentage, parts per million, and while we're here, parts per billion. Why miss any? So we were given the molarity 1.0 molar. Molality, by definition, means what? Moles solute per kilogram solvent. That's the really, really important idea. He's the only one that relates only to the solvent. And notice he's based on kilograms as well. So our moles of solute we have here, 1.0. This is grams, which means that I have 0.91544, whatever, kilograms. Our survey says 1.09 molal is how you would say that. Notice that the molarity and the molality are similar numbers. The more their density is close to 1, the closer they're going to be to one another, but they're not identical. But this gives you a seat of the pants knowledge of, does this number look reasonable? Your molality and your molarity should be the same order of magnitude. So let's have a look at our mole fraction. Remember, mole fraction could be based on anything. If I based it on the solute, then it would be 1 mole over a total of 51.81 moles. What do you come up with for that fraction? Okay. Now remember that the solvent then has to be 1 minus the solute, because they always have to add up to 1. So I don't have to do any more math than that. If you calculated 1 and you realized, oh darn it, I needed to do the other one, you can correct for that easily, because all the fractions have to add up to 1. So percentage, by definition, means what? Mass solute over mass solution. And since it's a percent, that means I'm going to multiply by 10 to the second. I use the same fraction. I just have different multipliers for parts per million and parts per billion. So for the first one, or 74.5513 of our solute, our total solution is 990 times 10 to the second. Gives you what percentage? Sounds about right. Now notice, from here to here, the only difference is we're multiplying by 10 to the fourth. 7.53 e to the fourth ppm. 7.53, another 3, right, times 10 to the third, e to the seventh ppm. As long as you know your definitions, then you're good. Questions? This would be a great time. Please stop me as we're moving along if there's anything that doesn't track for you, because this is something that needs to become natural for you. Right? So let's look at the next one. The reason I'm doing so many examples is that it's a matter of this very first step. This is the hard step right here. And if you don't take the time to analyze it at this very first step, then you're going to get lost. Remember that all concentrations give two ratios, or two pieces of information. And if you're looking at it and you're not seeing two pieces of information, then you're not rewriting it, which is what I'm doing here. My molality is telling me I have 1.0 moles of my solute, which is KCl. I know my solute is KCl because that's how they name the solution. They didn't say any other substance, so presumably our solvent is water. And we have an overall solution, which we know is the mixture or the total. When they gave me molality, that tells me moles per what? Kilogram of what? Solvent. And implied the number 1. Because everything's a fraction over 1 if there's no other denominator. Which means that when we're starting out, then I know 2 things. I know how many moles of this, and I know how much solvent I have. I also am given a density, which is my reference information for my solution. Since it's still water, still KCl, I did that just for time considerations here. Just checking my number. We okay? So taking this information, I can populate these two cells. So what goes in my moles of KCl? 1.0. What goes into my solvent? 1,000 grams or 1 kilogram. But since grams is where we're going to be working most of the time, it's nice to have that. Yes, because at some point, this is how many grams per mole, right? So you'd have to convert somewhere along the line. So my recommendation is you work with grams in this column. Just remember that this one's always going to give you kilograms. All right, so where can I start? Where do I have two pieces of information? I can find the mass of solute. I have 1 mole of KCl, and I know his molar mass. It says for every 1 mole, there's 74.5513 grams, because that's what molar mass tells me. Where could I go next? I could find moles of H2O because I have two pieces of information in that column. This time I have 1,000 grams of water. And I know that for every 18.0158 grams, there's 1 mole. What'd you get for that, Mary? Thank you. Where could I go next, Samantha? Your pick. Samantha, where could I go next? This is your pick. Okay. Do you find two things in the same row or column? Okay, so which one? Mass or moles? Or we don't have two things in this column. We do have all of this filled out, right? So the rows are coming across. So which one do you want to look at? Mass or moles? Okay, there you go. Because this column is always the total, all we do is add those two. So what's our total moles? And our total mass? There you go. Exactly right. Are we okay with that? Stop me if you're not. Only have one missing gap here. And remember that density only allows me to go between mass and volume. So if I need to go between these two cells, I have to use my density. What I know is that I have 1,074.5513 grams of solution. And my density is how many grams are in a milliliter of that solution. Anybody need Kleenex, Purell, hazmat suit, splash guards? What did we come up with? What did you come up with, Alex? $1.096 liters? Because we know at some point we're going to need that in liters. So these two, you're going to need maybe 2 different units. These two, you might need 2 different units, but how you get there is pretty much consistent. We okay so far? So molarity, molality, mole fraction, percentage, ppm, ppb. We know this one is 1.0 because we were given that one. Moles per kilogram. If I wanted to find molarity, what's my definition of that? Moles of solute over liters of solution. How many moles of solute do I have? 1.0. How many liters of solution do I have? 1.096. Again, pulling out of my solution column. So what'd you come up with for that, Morgan? Thank you very much. Again, notice that they're similar numbers. They're a little less similar because the density is starting to deviate a little bit more, but they're pretty close. If I were doing mole fraction, I'm going to go ahead and pick the solvent this time. Mr. Wynn, how would I set that one up? What's the definition? Not if I want solvent this time. So moles of solvent over, you had a 50-50 on that again. Check your definition. Over moles total. It's really not, this is not really, you can't have moles of a solution. This is moles total. It's just that the solution is the only one that's a mix. So in this case, that would be then 55.5 over 56.5. What do you get as a mole fraction? .98. Now, if I needed to know the solute, how would I find it? 1 minus 0.98. 0.02. So if you've solved for one, you always know the other one. No, because it's just a fraction. I mean, the moles over moles would have canceled in terms of units. Same thing with percentages because it's a mass over a mass. They never have any units other than that, their ratios. All right, so if you're talking about percentage, what's my definition of that? What do you think, Jalen? There you go. Okay, good. Mass solute over mass solution times 10 to the second. So for these numbers, what would that be? Jalen, what mass of solute do I have? And how much solution do I have? Times 10 to the second.
So we do the same thing if it was to the millions or to the billions, except just do it.
It's the same ratio times 10 to the 6 times 10 to the 9th. That's right. Because per means divided by. So they're just telling you which number to divide by. Since we're solving for the per, then we're multiplying the other fraction to isolate that variable. Anybody come up with a percentage? 0.1379? 9379. So this one then would be 9.379 e to the third and 9.379. 6 point, okay, sorry. This is what happens when I can't hear you. It's not your fault I got headsets on, that's hard. So times 10 to the 6.9379. Okay, so there's no multiplier. So 6.9379 times 10 to the fourth, because you can see this is 10 to the fourth times larger. From here to here is a 10 to the third times more. 6.9379. Getting a little better so far. So let's look at the next one. Mole fraction. We're told this time we have a mole fraction based on KCl, which tells us again that our solute is KCl. Presumably that our solvent is water. And then we have our solution, which is our total mixture. I know at some point I'm going to need to know mass in grams and moles, and I'm going to need to know volume. So in this problem, what three pieces of information do I know? That's one of, I know the moles of KCl. What else do I know? I know the density. And I know my total moles. Because by definition, this is moles of KCl over moles total. And if there isn't any other denominator, then it's presumed to be 1. 1 total if the other one is 0.060. And our density was given as 0.87 grams per milliliter. So if they don't tell you any other piece of information, remember this is an implied ratio. So you write that ratio out and it will make this problem much easier for you. Yes.
And then for the H2O solvent, I would just take the 1 minus the 0.06.
Absolutely. Because I know that these have to sum up to the one on the right. Where else can I go? I can get the mass of KCl, sure. Because this time I know I have 0.060 moles KCl, and I know it's molar mass that tells me for every 1 mole, because that's implied as well, there's 74.5513 grams. And what do we get there? That seems weird. Times 10 to the... Oh, you're right. Sorry. I'm totally good there. Again, I can't do math in the mornings. It's a thing. It is in my world. Check and see when I'm answering your emails and stuff. I'm up till 2 in the morning every day. And then I'm up at 6, so yeah, this is not. Yeah, it's just not good. I'm not gonna lie, it's not good. All right, so what am I gonna do next? For the solvent, I've got 0.94 moles of solvent, water. And I know this time that for every 1 mole, there's 18.0158. 16.93. Oh, yeah. Samantha, what can I find now? Exactly. So how am I going to do that? Absolutely. 21 point what? 40? I only have one unknown at this point. I know that I have to find my volume. This, remember, is a conversion. All of these are conversions. I can't start with a density. Reference information can only be used as a conversion. I have to start with what I know. Since density talks about mass and volume, then I'm going to start with the mass. I have 21.40 grams. My density says that there's 0.87 grams for every milliliter. So how many milliliters do I get? Okay. That's milliliters, which is 0.02459 liters, because I might need it in the other units as well. Molarity, molality, mole fraction, percentage, ppm, ppb. This time I knew my mole fraction, but if I wanted to know about my solvent, what would that be? 1 minus 0.06 or 0.94, because I was given the mole fraction of solute. Definition of molarity. What do you think, Patricia? What's my definition of molarity? Not if it's molarity. Listen to the word. It's molarity. It's not massarity. Right? So it is moles of solute over what? In what units? Liters of solution. So pay attention carefully to the words. Molarity, molality. They're trying to tell you what the numerator is. If I'm doing molality, that would be moles of solute over what? Kilograms of what? Solvent. So you can see that if you don't know these definitions, it gets very, very challenging. If you do know the definitions, then they're just plug and chug. By definition, how do I determine the percentage? Mass of solute over mass of solution times 10 to the second, same ratio times 10 to the what? 6th, and times 10 to the 9th, times a million times a billion. So based on our numbers, 0.060 over 0.02459 gives you what for a molarity? 0.060 over, now we had grams, 0.01693 kilograms. Our survey says. Same order of magnitude. They're still in the ones place. You can see they're starting to get a lot more different because the density is not as close to 1. What would I substitute in for my percentage, Ms. Chikwe? Okay, so what numbers? I agree. And our survey says 20.89 times 10 to the fourth, 2.089 times 10 to the fifth, another 3, 2.089 times 10 to the eighth. Are we okay so far? Stop me before I kill again. These are the ones that get weird. They get weird because of what they're called. This is called what? Percent. That means in your ratio, you have to divide by 100 by definition. So when they give you a percentage, it means your denominator is 100. If they gave you a ppm, what would your denominator be? 10 to the 6th. So that's why these ones are weird, because these are the only ones that have written into their name, divide by whatever the denominator is. So we're told in this case that it's 1.05%. That means 1.05 grams of KCl for every 100 grams of solution. Again, written into the name is telling you what the denominator is. Solute, solvent, solution, mass, moles, our reference information. So what do I know from my starting information then? I know the density. I know the mass of KCl. What else do I know? The mass of the total solution. 1.05, 100, and our density is 1.15 grams per milliliter. I'm going to need to know volume at some point. So where can I start? Yeah, easiest one is this one, the missing mass, because how does this relate to the other two? Yeah, total minus this one. So 100 minus 1.05, 98.95 grams, or 0.09895 kilograms, which we'll also need at some point. Where can I go now, Ugo? Ugo? You back there? Where can I go now? Okay. Doesn't really matter which one I go first. This one seems like a reasonable choice. I've got 1.05 grams. How am I going to set up that fraction? Thank you. And our survey says give me another sig fig at least.
It's 0.013.
What number did you put in here? Did you have 1.05
Yeah.
over 74.5513? I don't know. Check your numbers, folks.
Yeah, never mind.
Okay.
I got it.
Okay, so 1408. Okay. Just checking. All right, what else can we do? Moles of H2O. I've got 98.95 grams of it. How do I set up the fraction? I'm with you. And what'd you come up with? All right. Give me at least one more place. Okay. Where can I go from there? Total moles. What'd you come up with?
506.
All right. Thank you. If I need to find volume, what do I need to start with? I have to start with the mass. Again, this is just my conversion, so I have to start with either mass or volume when I'm going between these two. So what I have is mass. How do I use that relationship? Okay, so how do I use that? 1 mil on the top, 1.15 grams on the bottom. And our survey says drawing that out for suspense. Oh my gosh, what's it going to be? Right. And again, we're probably going to need that in liters. Space here. Molarity, molality, mole fraction, percentage, parts per million, parts per billion. This time we know our percentage was 1.05. So what's our part per million? Times 10 to the fourth. And to go to parts per billion from there, I'm going to multiply by 10 to the third more. Because this one was a times 10 to the second, times 10 to the sixth, times 10 to the ninth. So between these two, you have to multiply by 10 to the third. Right. So those are the easy ones. By definition, what is molarity? Moles of solute per liters of solution. You know the words of songs you don't even like because you hear them. So sing along with us. It will help you. It'll help you when you sit down to take a test. It'll help you when you're working on homework. So in this instance, moles of solute, 0.01408, liters of solution, 0.086957. Molality, 0.01408 over kilograms, 0.0986, or 895 rather. Mole fraction, depends on which one I'm talking about. If I talk about the solvent, That would be 5.492 over 5.506. But if I needed the solute, that would be 1 minus the other one. So what would we come up with for molarity? I'm sorry? 0.162 in our molality. Again, similar size numbers, similar to one another. Mole fraction of the solvent. Go and take 5 and we will come back. We're actually going to work in here for a little bit longer. Trust me on this. Certainly. Sorry, I'm working on it. That's everything's there. Yeah. We're going to stay here a little bit longer. Yes. Now you may, of course, may or may not have noticed how many days we lose because of holidays. That's why I have to take some of your lab time some days to do lecture. Otherwise, there's no way you can keep up. So we're going to spend a little bit more time on lecture, and then we'll go and do lab. There's a trade-off, and that is that I don't make you do as many trials on days like this because you can't. All right, colligative properties, by definition, are properties that depend only on what? From your reading. From your pre-reading? Oh, yes. Okay, well then feel free to look that up. Which brings us to things like normal boiling point. Normal boiling point is the boiling point, which is the temperature at which a liquid converts to gas at atmospheric pressure equal to 1 atmosphere. Because it turns out that if the atmospheric pressure changes, then you can get something to boil even at room temperature. Water will boil at room temperature with only a mild change in atmospheric pressure. So boiling point is a changeable number. It depends on the conditions. If we're just comparing what one variable does, then we would want the pressure to be constant. Most of the time we're working at atmospheric pressure or pretty close to 1 atmosphere. Boiling point elevation means that we have an increased boiling point due to contamination. And a freezing point depression means we should have a decreased freezing point. Remember that freezing point is the same thing as melting point due to contamination. Now, if you think about it for a couple minutes, you can actually sort of visualize why this might happen. Let's say that I want to boil something. So I've got this fluid in here, and to be a liquid, that means that it has some sort of intermolecular attractions to the other molecules in that mixture. And there's a certain amount of surface tension because of that as well. I'm sorry? Liquids to gas. Right? Boiling is when you're going from a liquid to a gas. So I've got this liquid. It has some intermolecular forces that are holding it together, and that's why it is a liquid. And when I want to boil it, 2 things have to happen. One of them is that I need to break these attractions apart. So I need to get these moving quickly enough, which is what temperature does, so that they're able to break apart from one another. So the first thing I have to do is I have to be able to break those intermolecular forces. But the second thing that I have to do is that I need to overcome atmospheric pressure. Because the whole time, there is a pressure from the atmosphere that's keeping those down into that liquid state. So to boil something, that's why it's changeable. If I reduce this amount of pressure, then it doesn't have to work quite so hard, and it can happen at a lower temperature. That's why the boiling point in Denver is lower. That at high altitude, you have lower pressures, and therefore it doesn't have to work so hard. All it has to do is break the intermolecular forces. But when we're seeing these elevations are always because of some contamination. Now, one application where we see this is Raoult's law, because the other half of the definition of a boiling point is this. A boiling point, and you may remember this from your Chem 2045, says that the vapor pressure of your liquid equals the atmospheric pressure. At this temperature. Back from 2045 days, you found that vapor pressures are an exponential relationship to temperature. The higher the temperature, the higher the vapor pressure, regardless of the substance. Now, how much it changes depends on the substance, but you always see a relationship like this. That was called totally skipping my brain today. Someday you'll go, Clausius-Clapeyron, there we go. You did Clausius-Clapeyron equations back in Gen Chem days. Vapor pressure increases with temperature in an exponential way. When the vapor pressure when the pressure pushing up from your vapor actually is at least the same as atmospheric pressure, then it can boil. If it's weaker than that, then it can't. And of course, the vapor pressure will depend on those intermolecular forces. That's why not every substance, something that has a very weak intermolecular force, would have a higher vapor pressure earlier on, whereas something that has stronger intermolecular forces. That's just because the atmospheric is changing. It doesn't affect the intermolecular forces. But yes, so that's really what the difference is between normal boiling point and any other boiling point, is that sea level, the atmospheric pressure is pretty close to 1 atmosphere. At higher altitudes, this number is changing. What we're looking at is that we're going to add contamination to our sample. That's not going to change what the atmosphere is doing. That's changing my mixture. This affects my vapor pressure. And that's what Raoult's law says. Raoult's law says the vapor pressure of a liquid varies as a function of its purity, where the x's here are mole fractions of substances. Typically, they're the mole fraction of that solvent. And P with the superscript 0 here, these should both be superscript zeros, and I don't know why it moves my superscripts around. P with the superscript 0 is the vapor pressure of the pure solvent. So this 0 at the top means that it's pure. So if I have only one substance that is volatile, volatile means easily vaporized, then I only have one substance to consider, the pure solvent, and then what fraction of it is that solvent. This is our fractional purity. If I have 2 volatile substances, then they'll each contribute. So if you have a solute that's also volatile, it could contribute to the overall vapor pressure. So you have one of these for every volatile substance in your mixture. How will you know if your substance is volatile? because in the question, they're going to tell you about its vapor pressure. If it's not volatile, they won't give you the vapor pressure. Therefore, it's not a factor there. So let's look at how this works. 2-methylheptane, and they gave us our molar mass, has a vapor pressure of 233.95 at 55 degrees. We mention that because it could be a different number at a different temperature. 3-ethylpentane, different substance. What we know about it is that his pure vapor pressure is 233.95. 3-ethylpentane, we also know his molar mass, 233.95. 3-ethylpentane, molar mass of 100.20, has a vapor pressure. So again, we know that it must be volatile, 207.68 at the same temperature. Question is, what would be the pressure of the mixture of 78.0 grams of this and 15 grams of that? $114. Wow, where did I get that number? Okay, I'm brain damaged. Yes. Sorry, guys, I really don't know what's the problem today. 114.23. Thank you. Are you with me? So thank you for asking about that. All right, so this time we have 2 volatile substances. For every volatile substance, I have another term. If I had 3 volatiles, then it would be X of A, P0 of A, X of B, P0 of that substance, X of C plus P0 of that substance. It could go on and on. So as many volatiles as I have, that's how many terms I need. In this case, I had 2 volatile substances because I had 2 pure vapor pressures. So I do need to figure out their mole fractions, which means that I need to figure out their moles. I know that for this one, I've got 78.0 grams divided by 114.23. For this one, I've got 15 grams divided by 100.20, which means that my total moles .8315. Are you with me? Stop me if you are not. So that lets me find my mole fraction of the first substance. It's going to be 0.6828 over our total. How will I find the mole fraction of the other substance? Good for you. There's only 2 things there. They have to add up to 1 because it's a fraction. So 1 minus 0.8212 would give us our other one. Alternately, if we were just dying to, we could have put in his own fraction. We had his own fraction of 0.1497 over the total. It's the same number. Right. So now we have the mole fractions for each thing. So the mole fraction of A, I'm going to call this one A, call this one B just for simplicity's sake. Mole fraction of A times his vapor pressure adds to the mole fraction of B times his vapor pressure to give us a total pressure. So 0.8212 times his pressure of 233.95 adds to the other one, which is 0.1788 times his pressure of 207.68. So apparently my vapor pressure is 229.25. Our units, because this was given to us as torr, are still torr. Because a fraction of something that's in torr, because this has no units, would give us an answer in torrs. Notice that it's going to be somewhere between these two numbers. It should be. It's really sort of a weighted average. Notice that it's closer to this number because it has a higher contribution. Now, where do we use this? We use this when we're talking about your radiator. Why do we put antifreeze into your car? Because we don't want the radiator to explode. We don't want to lose all of the water that's used as a coolant. So we put antifreeze in here. We intentionally add a contaminant so that it reduces the vapor pressure. And therefore it doesn't boil off as easily. So let's look at the next one here. Substance A is my 2-methylhexane here. What we know about it is that it has a molar mass of 100.20 grams per mole. And we know his pure vapor pressure is 37.986 torr. Substance B here is we have naphthalene. What we know about the substances is that I have 78 grams of this, and I have 15 grams of this, and they gave us a molar mass 128.17 grams per mole. What did they not give us? The vapor pressure. They did, in fact, tell us that it's pretty much non-volatile. It's not a contributor here. So my total is going to be based on just one thing, because I don't have two volatiles. But I do need to know how much I had so that I can find my mole fraction. .78 divided by 100.20. 15 divided by 128.17. Total 0.7784 adds to 0.117. So what's my mole fraction? How do I set that up? Which are what number? .7784 over 0.8954. So I just find my mole fraction, and now I can substitute in. 0.8693 is my mole fraction times my vapor pressure, if it's pure, is 37.986. Gives me 33 torr. So adding a contaminant, regardless of what that contaminant is, lowered my vapor pressure. If it was pure, it would have built up roughly 38 torr. But by adding that contaminant, it's now dropped down to 32. So impurities will always reduce your vapor pressure. It is. You added a contaminant, which would change your vapor pressure. Now, vapor pressure has a bigger effect on your melting or on your boiling point, but it's the same idea. Now, so why did this happen? Well, physiologically or physically in your sample, it's trying to build up pressure. Why does it change it? Because it has to be able to get to the surface. If I have some impurity that's floating around and blocking surface access, it can't escape. That's why adding the impurity makes it heat up longer, because it's going to take a lot more time before they can all get to the surface to actually escape. So you're physically blocking. This is why when you are cooking pasta, they have you adding oil to it or they have you adding salt to it. And that's to actually create an impurity so that it's going to boil a little bit higher. And that little bit higher, it doesn't have to be a lot of difference. It turns out that for pasta, like a 0.1 degree difference Celsius will make the difference between whether your pasta is mushy and whether it is actually al dente the way you want it. So it makes a difference. It doesn't really matter what kind of impurity you have. You just want to introduce some impurity. So a couple things happen. It's not just the boiling points that change. Back in 2045, you talked about phase diagrams. And the one in blue is what would happen if it were pure. If I add an impurity, it moves my boiling point a little bit farther to the right, a little bit higher temperature. But notice that it makes my melting point move a little bit down. This is our freezing point depression. And this is our boiling point elevation. An impurity changes the vapor pressure. Therefore, while it's trying to build up enough pressure to actually boil, it's heating up, it's continuing to add to the temperature. And so your phase diagram changes when you have an impurity, and that's always going to happen. Solid, liquid, gas in general, if you don't remember that about phase diagrams. So regardless of the identity of the particles, it's really all about what the mole fraction is. It didn't matter what it was, it just mattered what fraction you have. Now, when you're talking about specific effects on the freezing point or the boiling point, we're going to use the same equation. Now, I have no idea why your book makes this it gives you multiple equations for exactly the same idea. We're not going to do that. We're going to work with one equation. Whether you're talking about freezing point or melting point or boiling point, it's still the same equation. This is super, super important here. Delta T in this equation is always mix minus pure. The number one problem that students have with this is reversing which one they're talking about. Part of it is because of how the K's are tabulated, and we'll come back to that. What we're saying is that the amount that the temperature is going to change, if I compare the mixture to the pure substance, the amount that the temperature is going to change at which it boils or which it freezes depends on the concentration, depends on the molality. Notice which one they gave you. It also depends on the solvent. So this K value is specific to the solvent. Now, again, your book gives you two different equations, and then it changes the orders of these. If we only work with one equation, it's simpler. And if it's always mix minus pure, it always works. The difference is that the K values are positive if I'm talking about boiling, because you can see that that's a positive change. And the K values should be negative if I'm talking about freezing point. So by putting the sign on these, then you can always say mix minus pure. You can use the same equation. It'll always work. Which brings us to this little I thing here. This is a preview. For whatever reason, this textbook and many others holds off on this discussion until the very end of the chapter, and it doesn't make sense. I is called the Van Hoff factor. This says when a substance is dissolved, if they dissociate, then that means you have more particles than the undissolved substance. So if I'm talking about something like sodium chloride, solid, and I had 1 mole of this, then I have 1 mole of these particles. If I'm talking about sodium chloride aqueous, when it's aqueous, this dissociates. I now have 2 moles of particles. This I is saying, how many particles are you getting? If I were talking about something like aluminum chloride, when this is aqueous, I have aluminum ions and 3 chloride ions. In total, I have 4 ions. Did you agree to that? So I for this would be 4. If I is non-ionic or a weak electrolyte, or even better, a non-electrolyte, then it's pretty much 1. But if it's something that breaks apart, then that's going to show up. So I mention it now because it makes sense to talk about it now, since we're talking about the only equation that uses it to a large amount. Now, the boiling point and freezing point constants are always given to you. You don't have to memorize these numbers. You just need to know how they work. And in your reference pack, they're right there, right under your formula sheets. Freezing point constant, notice it's positive for boiling. It's negative if we're talking about freezing, and it depends on what solvent you're working with. So let's see now. So this is a real antifreeze. This is called Sierra Antifreeze. I went to their website and I looked to see what specifications they gave. And they said that if you make a 40-60 solution of Sierra Antifreeze and water, that you'd have a -4 degrees freezing point. Now, they said 40-60, usually that means by volume. So we're going to figure out what is, instead of using this ratio, we're going to figure out what the actual concentration is that would do such a thing. Well, first off, if you look at your freezing point constants, they're given relative to Celsius temperatures. And so the units here would be like degrees Celsius per molal. And so we need to take this information and convert it to Celsius. I know that Fahrenheit is 1.8 times degrees Celsius plus 32. So -4 minus 32 is 1.8 times degrees Celsius. Minus 36 divided by 1.8 equals my degrees Celsius. Apparently, my temperature is, for my mixture, -20. Because it was a mixture that gave me that. So what's the normal freezing point for pure water? Zero. Are you with me? So delta T equals IMK. Since we're talking about freezing point, we're going to use the K for the freezing point. We know that delta T is always mixed minus pure. So -20 minus 0. Now, we don't know anything about this antifreeze, so we're going to assume that I is equal to 1. If you read a little further, you'll find that most antifreezes are non-ionic. If they were ionic, they would corrode your radiator. because anytime you have moving ions, it creates an electrical charge, and that hastens redox reactions. So we know that this is probably non-ionic. We don't know the molality, that's what we're looking for. But we do know the freezing point constant for water because it's on our reference pack. For water, the freezing point constant is minus 1.85. Again, the units are degrees Celsius per molal. Per molal. Lowercase m, which is why that can work out in terms of units. So negative 20 on the left divided by negative 1.85 degrees Celsius per molal will give us our molality. And what do we come up with? Can't be negative. 10.81 though, I would totally agree with. I'm sorry? Anybody else get 10.81? Okay, that sounds normal. That sounds right to me. It's been a couple semesters. But... All right, so let's look at the next portion of it. We have a mixture, 42 grams of the antifreeze, 60 grams of the water. We know its freezing point is this, and we want to know what is the molar mass. Let me give you a little clue. If it has the same freezing point, it has to be the same concentration. Because that's the thing about colligative properties. Doesn't matter what it is, just matters how much it is. And any concentration would give you the same, that would give you the same freezing point must be the same concentration. You could prove it to yourself. Now let's see what we can know from this. If I know that I have 10.81 moles of this antifreeze per kilogram of my solvent, you agree to that? That's what molality means. And I actually know how much water I have. Do you agree that water has to be my solvent because there's more of it? That tells me how many moles of my antifreeze I have. Six, 4, 8. Okay. Now, what units are associated with molar mass? That's how many grams there are for every mole. Do I know how many grams there are of the antifreeze? Sure. I have 42 grams of it. And I have 0.6486 moles of it. And so we actually can figure out what its molar mass is. Grams per mole. Sorry. I don't know why it does that just randomly. Now, next one says, if the freezing point is -4, what would be its boiling point? Again, if it has the same freezing point, it has to be the same concentration. So we still know that the molality is 10.81. The question's asking, what is the boiling point? Delta T equals IMK for my boiling point. we're looking for the boiling point of the mixture. Don't know that. But what's the boiling point of pure water? 100 degrees Celsius, yes. I is still 1. Our molality is 10.81 degrees Celsius per molal. But this time, since we're talking about the boiling point, we have to use its constant. .5121. Hello. I have no idea what is wrong with my brain today. It's just on slow-mo. Feel free to change the units of the last one. So we're substituting in T mix we're looking for. We know the pure. We know I is 1. Molality is still the same because it was the same freezing point, same solution. This time we're seeing how that same concentration would give us a difference in the freezing point. So T mix is going to be 100 plus those numbers. And what do we come up with? Sounds about right. Notice that when we were talking about freezing point, the mixture freezing point was lower than the pure. That's why we call it freezing point depression. If we're talking about boiling point, it's always going to be higher than the pure because it's called boiling point elevation. So the boiling points always go up, the freezing points always go down, and the only question is what concentration of contaminant do you have? So if we're talking about that pasta example, I've got about 15 grams of salt in about 2 liters of water. So clearly water is my solvent. I know of my solvent, it's about 2 liters. Since I need to know molality, I'm going to work with the density of water. Density of water is 1 gram per milliliter. So that's about 2,000 milliliters, which gives us about 2,000 grams of water. Usually we're given mass information in the definitions, but this time we were given volume. For any pure substance, I can go between volume and mass using the density. So what I need to know is what is the expected boiling point? Boiling point of a mixture is always going to be determined by this equation. T mix is what I'm looking for. What is the boiling point of pure water again? 100. This time our solute is NaCl. What is I for this? 2. When this breaks apart, I get 2 ions, yes? So I get twice the effect. I need to have the concentration in molality, which means that I need to know how many moles of solute and how many kilograms of solvent. Well, I know how much solvent I have. It's going to be 2 kilograms. But I do have to take a moment and figure out my moles of this. Molar mass is 58.44. So 15 grams, 58.44 grams per mole gives me how many moles of sodium chloride? Point 257. Okay. So 0.257 moles of sodium chloride in 2 kilograms of solvent is our molality. Boiling point constant we just looked up for water was positive 0.5121 degrees Celsius per molal. So T for our mix is going to be 100 plus all of that. And what do you come up with? Okay, so 0.26 for all of this stuff. So 100.26 degrees Celsius. So 15 grams, by the way, is about a teaspoon. That means that the shaker amount that you're using, which is about an eighth of that, still makes enough of a difference, but it's not a huge difference. It's just enough for pasta. Fun fact about that. All right, so let's take a moment and relate this to the lab that you did. If you look at the first experiment for what you did, you had pure stearic acid. And the whole purpose of this graph was to figure out at what temperature it converted. Now, if you watch the video, it tells you how to analyze your graph. You need to find a line that correlates to your decline. You need to find a line that correlates to your plateau. And where they intersect, that's the temperature, that's the freezing point. So the whole purpose of experiment 1 was just to find the freezing point for pure stearic acid. Then you did experiment 2 where you had a contaminant. In experiment 2, because you knew what the substance was, you were able to find the freezing point of the mix. So we know the freezing point. And we're able to find the molality of the mixture because we know what it is. We made it. We know how much of everything we used. The only question here was, what's the K value for the freezing point constant? Because it's not readily available. So you measured this. You made a known mixture, known substance, and you saw how it affected the freezing point. And the whole purpose of experiment 2 was to come up with a K for stearic acid. Yeah. It's molality. It's still molality, and it's always your solute. If you look at the contaminant, you had 1 gram of biphenyl in 6 grams of stearic acid. So the biphenyl clearly is your solute. When you looked at experiment 3, you had a freezing point of a mixture that you're going to get off the graph. This time, you know the K because you figured that out in the last step. And your task here is to find the molality. And because you know how much of everything you used, you're going to find the molar mass of your unknown, which is a lot like this problem. And this problem, we knew the molality because we got it from the last problem. And we solved for the molar mass. Because you knew how much you mixed, you knew these numbers, so you were able to make that conversion. So that is what your lab is asking you to do for the freezing point constant. There's a video on it if you have not yet looked on it, and that's where we're going to quit. Meet you down in the lab in about 10 minutes.